Hi, we would like to thank you for your time and interest in watching this video on advancing oleochemical fractionation, from modeling work to pilot plant. The global oleochemicals market size continues to grow. It is anticipated to be the most profitable regional market in the future. However, one of the main issues surrounding the palm oil industry is sustainability. Over the years, palm oil players around the world are undoubtedly promoting sustainability. Despite various exertions, reducing the associated energy is still a continuing concern. Ultimately, for the industry to stay competitive and sustainable, there is potential energy saving that can be made along with the reduction in greenhouse gas emissions. One of them is by improving the fractionation process. Distillation column is the most common thermal separation unit in chemical industries. It is commonly known that the distillations consume 40% of the total plant energy. Although it existed thousands of years ago, researchers today are still motivated to develop and improve the efficiency of distillation processes through various approaches including intensification, heat integration, optimization, etc. Dividing wall column or DWC is a form of intensified distillation column and has been used for the past 18 years. DWC has an advantage for separating multi-component mixtures with reduced cost and energy consumption. It is expected that in the next decades DWC will become the standard in the chemical industry. Distillation columns dominate the oleochemical fractionation process. Our survey from 12 oleochemical plants shows that fractionation processes were done using conventional distillation columns. Unlike the oil and gas industry, acceptance of DWC is particularly slow in the oleochemical industry. This is due to lack of a systematic design approach, operational experience and knowledge. But if done properly and systematically, DWC could offer huge opportunities. Therefore, this work attempts to rectify the deficiencies by providing an exciting opportunity to advance the understanding of this growing area of research. Our work will focus on using state-of-the-art sequential modular modeling and simulation approaches in Aspen+. For this presentation, we will focus on the following topic. First, is on modeling, simulation and analysis of DWC performance. The case study will be fractionation of oleochemical fatty acid. Economic and environmental analysis were performed and compared. Second topic will focus on dynamic modeling in Aspen Dynamics. Third topic is on process flowsheet optimization where statistical experimental design approach will be used alongside with the developed Aspen Plus model. Lastly will be on the development of the pilot plant and how Aspen Plus was utilized to aid the development. We believe such work would undoubtedly reduce the odds of setback during the early stage of development and accelerate industrial scale application. DWC model block is not readily available in Aspen Plus and had to be customized. A DWC model is built on 4 red frac blocks representing 4 internal sections of DWC with a condenser, a reboiler as well as a liquid and vapor splitter. These blocks were connected with interconnecting input-output streams which creates complex interactions. This however causes convergence problems and requires a lot of parameter tweaking and tuning. In one of our papers, we introduced step-by-step design procedures from shortcut to rigorous model to aid in the design, model and simulate a DWC. The oleochemical product that we used as our case study is fatty acid from refined bleached deodorized palm kernel oil. There are 4 main cuts to be fractionated which are pre-cut C6 to C8, light cut C10 to C12, middle cut C14 and heavy cut C16 to C18. Apart from fatty acid, residues such as triglyceride were also included in the process. It is important to note that, to avoid product degradation, the temperature of the column needs to be operated under 260 degrees Celsius with vacuum pressure between 10 to 40 millibars. We perform a comparison between typical DC with DWC in fractionating the fatty acid. For the former a series of 4 DCs were used while the latter used 2 DWCs in series. The product specifications were set to 99% weight of pre-cut, light cut and middle cut and minimum of 99% weight of heavy cut. Packing sizing with column pressure updates were included in the model. It is quite straightforward for a typical distillation column, but for the DWC model several transfer blocks were added to prevent negative pressure and ensure pressure consistency. Reboiler and condenser design and costs were calculated using Aspen EDR, while environmental analysis was done using carbon tracking tools. The results are very promising. Although a slight advantage of 3.1% capital cost reduction over conventional distillation columns, further detail shows DWC reduces 16.8% and 7.3% in condenser and reboiler capital cost, respectively. Nevertheless, the major advantage can be seen in the operating cost, with 16.9% and 10.2% savings on cooling and heating utilities. The utilities savings also affect the CO2 emissions, with significant reduction of 10.2%. This clearly shows the leverage of DWC over conventional approach of fractionation. In addition to the steady-state modeling, a dynamic model of DWC was developed using Aspen Dynamics. The aim was to study the dynamic response and control performance analysis. Relative gain array and singular value analysis were performed in Aspen Plus to select suitable control loop pairing and configuration. To obtain more realistic results, a pressure-driven model was applied upon conversion to Aspen Dynamics. The identified control loop was added prior to performance analysis for set point tracking and disturbance rejection. Dynamic model was successfully performed in Aspen Dynamics. Based on relative gain array and singular value analysis, DSV control configuration was selected and gives the best performance for disturbance rejection and set point changes. Identification of suitable control configuration is important to ensure good plant operability. The dynamic model in Aspen Dynamics can be extended to other applications such as advanced process control, process trainers, and operator training simulator. For flowsheet optimization, a statistical-based experimental design approach was applied. Compared to model-based optimization, experimental design does not require mathematical formulation but nevertheless requires a good simulation model or experimental setup. Using the same case study, Taguchi method was applied, whereas the DWC model was used to identify sensitive parameters, simulate experimental layout trials, and results validation. The response variables were product purities, whereas the control variables were reflux ratio, liquid split, vapor split, and reboiler duty. An L25 orthogonal array was adopted, and the simulation run results were analyzed using signal-to-noise ratio. It is found that the most contributing variables that affect the product purity were liquid split ratio and reboiler duty. The use of experimental design approach to optimization significantly reduces the extensive effort of mathematical development, especially for complex processes. It also requires fewer runs and iteration, thus avoiding computational complexity. However, it might not be as accurate, precise, and extensive as mathematical model-based optimization, since the latter accounts for process phenomena through mass, equilibrium, summation, and enthalpy equations. Overall, our study demonstrates the successful integration of experimental design-based methods utilizing complex models developed using process simulators, for a simple, fast, and non-tedious approach for process optimization. Pilot plant development is an essential step prior to industrial application, where it can offer operational data which cannot be obtained through modeling or simulation alone. The pilot plant was built using interchangeable borosilicate glass parts with total height over 9 meters and column diameter between 4 to 8 inches. Industrial structure packings, sponsored by Sulzer, were installed inside the column. The divided section was equipped with a pneumatic reflux divider to split the rectification liquid. The pilot plant has been tested for other applications and has won several awards. The successful development was contributed by the use of Aspen Plus. Along the development phase, Plus has aided in the column design and sizing, sensitivity analysis, packing design and rating, and hydrodynamics, which helped to build the pilot plant. Undoubtedly, we believe the use of process simulators is imperative to close the gap between concept and actual applications. This in return would certainly reduce the odds of setback during the early stage of development and accelerate industrial scale application. We would like to thank those who have contributed to this work. Special thanks to the Department of Higher Education Malaysia and University Malaysia Pahang for their financial support. Last but not least, thank you AspenTech for giving us the opportunity to present our work in Beyond Optimized 21. Thank you for watching.